Go ahead.
Thank you, Simon. Yes, this is kind of preliminary work, so I'm very interested to hear feedback and get thoughts from everyone on this work. And my co-authors really haven't seen this, so if there are any mistakes or problems, that's on me. It's not their fault. So I sent the title in when we were first planning the meeting. I sent my title and abstract as how sensitive is the subpolar North Atlantic to changes in surface forcing. And as the meeting date got closer, I decided to focus on something much more specific, which Simon mentioned in his talk briefly before the coffee break, specifically on the 2014-2015 cold anomaly. So I'm zooming in a bit. It's not really multi-decadal variability. I'm cheating a little bit, but it's still, I think it's interesting. And as Simon pointed out, it can still be part of the larger kind of story of longer term variability. So here's a figure from Simon's review paper where he talked about this anomaly in the white box area there. The stippling indicates regions which are record low annual mean sea surface temperature spots since 1950. This is in the year 2015 from HAD ISST in that year, 2015. So you can see this really cold sea surface temperature anomaly sitting there. And Simon had a lot of thoughts about the possible causes of it and did a nice job writing the review. You can find, this is the tool that I've been using for ACSIS, is this ECHO version 4 release 3 state estimate. It's an observationally constrained state estimate. It's been nudged in a physically consistent way to agree with observations without using any sources or sinks of heat or salt. So it satisfies all the conservation laws, and you can do budget calculations with it, which is one of the nicest things about state estimates. So here is the 30-day mean and 360-day centered mean for various years of the heat content anomaly. And you do see, I've got it shaded here, starting about December 2013, there's this enormous drop in heat content that's pretty persistent for the next couple of years. It's there, it's present. So it's kind of great that it's present and in there, because it means we can now do heat budgets and we can ask questions about, well, what is causing that? Where does that huge drop in heat content come from? So here's a view. You're looking in depth on the vertical, and this is just a few years on the horizontal now, the potential temperature anomaly. And I was so excited to see Simon's schematic that he put up of reemergence, because I knew I had this figure coming up, which is reemergence. So there's the mixed layer depth with the seasonal cycle intact. The potential temperature anomalies have the monthly means removed. So you can see 2013, 2014, this cold anomaly shows up above the mixed layer and gets mixed downward. And then as the mixed layer shoals, the cold anomaly is still there, still sitting there underneath the mixed layer. It hangs out, waits until the next winter, and the next winter comes along and mixes that cold anomaly back up to the surface, as described in various papers by Michael Alexander a little while ago. So you can see how in 2015 that cold anomaly signal gets right up to the surface, which then becomes that 2015 cold anomaly. So reemergence is absolutely a part of the story here. The nice thing about having the state estimate, like I said, is you can do heat budgets. So you can map the total tendency and you can pull it apart into different components. So here, 2014, 2015, this is the total tendency you're looking at here in the color scale. So you can see there's a strong cooling kind of extending from the above the mixed layer down below the mixed layer, and then it gets mixed below that mixing layer there where it persists. So that's really where the kind of onset of the cold anomaly occurs. I did a heat budget, and I'm excited to show you the results. So what you're looking at is the heat content tendency. So that's the rate of change, right, of the heat content. And from 2012 to 2016, the black line is the total tendency, and the three components here, you've got the effective contribution in red, the diffusive contribution there, and the forcing contribution in blue. And just looking at the few months mean here, the local forcing, which is the forcing term, that's the cause of about 57% of that total cooling rate, not the cooling, but the rate of cooling. Advections of 44%, and it's very slightly offset by diffusion, 1%. Diffusion starts to go the other way. So big cooling anomaly over January, February, March 2014, which is consistent with what Simon has said. Here's the integrated rate of change. So it is just heat content. And what matters here is not so much where the lines are, but the change in the lines. That's really what you want to look at. So the total contribution, you can see the total going down there, indicating, yeah, there's some heat loss. And you can see that the forcing contribution makes a little bit of a jump there from, I should be using the cursor, shouldn't I? So for the people online, yeah. So here's the total drop from December 2013 here to December 2014, big drop. The forcing contribution makes that much of a contribution, which turns out that's only 30% of the total drop. And the advective contribution, although it's not quite as steep, it carries over for a longer period of time. So the total drop, that's 85% of the total drop there, occurring over that whole time period, that whole 1 year time period. And the diffusion, even though the rate is small, leads to about a warming 15% of that total drop. But going in the other direction, it's partially offset by that warming. So I was really happy to do that. That leads me to the question, though, how much of that advective transport coming in, how much of that is just a forcing-induced cold anomaly caused elsewhere that is then advected into our control volume? And to address that question, one of the possible ways to address that is to use an adjoint model. And just to remind you, the way that an adjoint model works, you can do these experiments where you ask how a given output depends on all the inputs. So here is the one of the outputs, the heat content integrated over a certain distance, that white volume, that white box that I showed you, the top 500 meters, and you integrate it in time. We decided to do the start of 2014 to the start of 2015. Give it a second and that bar will go away, I think. Yeah, there we go. And the adjoint model, which is, again, Echo V4R3, calculates the sensitivities of that quantity to all the different inputs. I focused on wind stress and on net heat flux. You get these time-evolving maps of partial derivatives that show you how the quantity J on the heat content depends on wind stress, depends on heat flux, and those patterns spread out. The further back in time you go, the wider the spatial coverage. Typically, it involves more and more of the ocean. So I'm going to be showing you some results from that. You can use the adjoint to get these source waters, which I really like. So this is just this is December 2013, so just before the start of that integration period, showing you these are all the waters that could potentially influence, just by direct kind of advection, the heat content in our black volume, in our control volume there, which is the cold blob region. So you do see the Gulf Stream feeds it, the NAC feeds it, the Labrador Sea, the Erminger Sea. All of those are potential source regions on this time scale. And if you look further back in time, that red pattern gets bigger and bigger and bigger and involves more and more of the ocean. So these are adjoint impacts. These are impacts of heat flux anomalies, 14-day mean heat flux anomalies on the control volume, on the big blue blob. So it gives you an idea of where and when those heat flux anomalies had the biggest impact on the actual heat content that you end up with. So the blue shading indicates places where an anomaly eventually leads to cooling. A heat flux anomaly eventually has led to cooling. So looking in December 2013, these are the regions that are involved. That's when that kind of strong cooling started, and you can see that it's still kind of local. It extends a little bit to the southwest of our control volume, but it's still kind of local on those timescales. Here's March 2012. I wanted to include this because I knew I'd be following the talk about the Erminger Sea. So the Erminger Sea is a deep convection region in here, and it does influence the heat content of that box. Wind stress looks interesting because wind stress has all these dipoles, and that's pretty typical of adjoint fields. You get dipoles all over the place, typically indicating places where the changes in wind stress are changing Ekman convergence and Ekman divergence, and therefore Ekman upwelling and downwelling, and it's possibly changing the kind of structure of the isopycnals and the dynamics through all of that. So it gives you lots of partially offset tendencies. But to go back to the question that I posed, how much of that temperature change is really just due to anomalies, surface forcing anomalies getting advected into our control volume? Well, you can start to address these questions. Sorry, my little bar is in the way there. Maybe I can drag it over here. Okay, so on the horizontal, when the bar goes away, you're looking at different years. And you should read this plot right to left. This is a cumulative sensitivity plot. I've just added up all of those sensitivities. And I've broken the total forcing contribution into local and non-local components. So as you're reading from right to left, you can see that the total forcing, let's try this again. Can I just get you to go away? This one? Dock and top. There we go. Hooray, that looks better. Okay, so the local contribution, you can kind of see is the blue line there. And what you want to look for in this plot is changes. So the biggest changes are where the biggest contributions are happening. So the local contribution happens during that super cold, that region of big cooling, but then it doesn't really do much after that. The non-local contribution is pretty big over the cooling period, but then it continues to contribute all the way back even to 2010. So when non-local forcing anomalies, even way back in 2010, can be thought of as having contributed to the cold anomaly, at least by this metric here. I broke it up by wind stress and heat flux. It's mostly wind stress, mostly non-local wind stress in terms of the total forcing had the biggest impact on the cold anomaly by this metric in this kind of sensitivity study, because you can see the heat flux contribution had a little jump there, little drop, and then not very much happened after that. The wind stress contribution was pretty big, but then it continued. So again, we're seeing this kind of story over and over again of there's the rates of these changes, and then even the things that change more slowly, if they happen over a longer and longer period of time, the cumulative effects can actually be bigger than the big flashy heat flux potentially. So how am I doing on time?
It's gone, about 2 minutes.
About 2, okay, well that's fine. So again, this is preliminary work. This is preliminary initial work, and I'm very happy to hear everyone's thoughts on it. Just to give you a quick summary, so basically my takeaway from doing the heat budget analysis was that advection is the biggest contributor to that cold blob anomaly, but the advection, some of that could include advection of nearby anomalies that were caused by heat flux. So I'm finding that wind stress has the mostly non-local wind stress is making a big contribution to that cold anomaly according to these adjoint results, and it'll be interesting to dig into that a little bit more. Going forward, I'd like to do some additional focused adjoint sensitivity experiments to one thing like full column depth. I want to do full column depth to get rid of the possibility that isopycnals might just be, Helen knows this this problem. Isopycnals moving into and out of the control volume, which is absolutely a thing to think about when you're looking at adjoint results, and to better synthesize what I got out of the heat budget and the sensitivity information. I also have an adjoint study where I'm looking at the sensitivity of the subpolar ocean heat content to different surface forcing, and I have some fields for that. I just for this talk, this made a more coherent story, I thought, so I decided to present this instead of the subpolar ocean heat content work. But I'll stop there.
Thanks very much, Doug. In the next speaker, Adrian, nothing obviously to change. Oh yes, yeah.
Can we look at that cumulative plot to that? Either of those. I mean, the red thing, the non-local forcing. If you picked a different area of the North Atlantic, would you still see something like that, or is that just confined to your control area?
Yes, if you change the control volume, that will look a bit different. So that does need to be part of how you interpret that. You could pick a bigger control volume, and then it's possible the non-local contribution wouldn't be as big. So yes, that is something to think about when you're interpreting the results.
What I'm really sorry, I'm not sure I understand exactly what you've done, but the point is, what's unique? Can you use plots like that to define what's unique about your area that is below one area?
Can we use the cumulative plots to define what's unique about a particular area, like to identify? I guess you would need to do some comparative studies, wouldn't you? You'd need to compare that with other adjoint results and see, oh, this region is particularly influenced, it's particularly local versus particularly non-local. I think you could. I think you would need to do several adjoint runs. That's kind of my initial thought to that question. But yeah, I like that.
I had a comment to that. So, because when we talked about this a couple of months ago, one aspect of this was to take some different domains of the Atlantic, hidden down different vector terms. So I guess that's what you've got in your mind as another thing going forwards, hopefully, to try and separate out that vector term into different contributions from the north and west and south, etc.
Yes.
Yeah.
Oh, and perhaps you may have also been, were you thinking more of, can you do that same kind of split in different regions and say, well, here's how much the Labrador Sea contributes and here's how much the Erminger Sea contributes,
I'm not sure
you
I
know?
thought that far.
Okay, yeah, because you can, and I have some of that.
Let's move to
Yeah.
John, because I think still got your hand up. John at the back.
So you said it's been really wet. My thoughts about it. Do you have a feeling for what processes have been forcing? Is it just local or relatively local economized urgings or upland, or is it changing the guide related to curve?
I'm not sure. What I usually like to do at this stage, like we did with the Labrador paper, is design some forward perturbation experiments and kick the system based on the fields that you see, and then you can really start to dig into the physics a bit more because you see, oh, the gyre is spinning up or slowing down. So that would be a next logical step for me with this work.